Let's take a look at a problem involving Newton's second law of rotation and Newton's second law of translation. Suppose we're in space, maybe in the space shuttle or the International Space Station, and we have this coffee can, and we have a string wrapped around it, and I'm not holding it with my left hand. This is just floating in the International Space Station. And I exert a force via this string, like this. Let's apply Newton's second law. We have a hoop of mass m, radius r, and an applied force. From Newton's second law of translation, we can write sigma F equals ma, so the force applied is equal to the mass of the hoop times the acceleration of its center of mass. Now let's apply Newton's second law of rotation. Net torque about any axis is equal to the moment of inertia about that axis times the angular acceleration. Let's sum torques about the center of mass. So we have the force times the moment arm, R, is equal to I, which is mr squared for a hoop, multiplied by the angular acceleration. So the hoop will accelerate translationally and it will accelerate rotationally. Let's return to this problem where I exerted a force on a hoop while it was in a state of free fall or in a zero gravity environment. Okay, we wrote this expression using Newton's second law of translation and this expression using Newton's second law of rotation. Now, if we combine these two equations, let's say solve this for force and then substitute it into here, we get a relationship between the acceleration of the hoop center of mass and the angular acceleration. Which is very interesting, because what this tells us is that if this hoop is pulled along a surface instead, so if I accelerate this hoop along this tabletop like this, isn't this identical to accelerating the hoop in space? So we can conclude that since there was no friction when I pulled this along in space, then there would be no friction between the tabletop and the hoop when I accelerated across the table.